December 27th, 2004. A pulse of energy arrived at Earth. It came from something 50,000 light-years away, on the far side of our own galaxy. It lasted 0.2 seconds, and it ionized Earth's ionosphere on the night side, the hemisphere facing away from the Sun, the way only direct sunlight normally does. Something from the other side of the Milky Way reached into Earth's atmosphere and changed it. The object that did this is 20 kilometers wide. That's the size of a city, not a star, a city. And it has a magnetic field so extreme that if you placed one 1,000 kilometers from Earth, the distance from London to Istanbul, the distance from New York to Indiana, the iron in your blood would be ripped through your skin before you finished your next thought. Not from heat, not from radiation alone, from the magnetic field itself, directly restructuring the atoms that make up your body. That object is called a magnetar. And I want to make sure that by the time we're done here, you understand not just what it is, but what it means for physics, for our place in the galaxy, and for what the universe is apparently capable of producing without anyone asking permission. Let's start with the baseline. Because a magnetar is extreme even by the standards of extreme, a neutron star is already the most compressed object that physically exists, a star that has collapsed to nuclear density, the same density as the nucleus of an atom, stretched across a sphere 20 kilometers wide. The mass of the Sun compressed into the size of a city. Surface gravity 200 billion times stronger than Earth's. 1 teaspoon of the material, 1 billion tons. The crust of a neutron star, a phase of matter called nuclear pasta, where neutrons are packed into sheets and tubes and lattices under pressures that would destroy any other material, is the strongest substance in the known universe, roughly 10 billion times stronger than steel. This is the floor, the baseline, the least extreme version of this class of object. Most neutron stars have magnetic fields between 10 to the 8th and 10 to the 12th Gauss. Earth's magnetic field is about half a Gauss. So an ordinary neutron star is already somewhere between 100 million and 1 trillion times more magnetic than Earth. That's the normal range for these objects. A magnetar has a field of 10 to the 14th to 10 to the 15th Gauss, 1,000 times beyond the strongest ordinary neutron star, a quadrillion times beyond Earth. And here's the thing, this is not just a bigger number. At these field strengths, the physics doesn't just scale up, it changes, qualitatively. New phenomena emerge that simply don't exist at lower field strengths. The magnetic field at this intensity doesn't just exert forces on matter, it restructures matter, it restructures space. Let me be specific about what I mean. In a magnetic field of 10 to the 15th power Gauss, atoms are not spherical. The electrons, forced by the field into what physicists call the lowest Landau level, compress into long, thin cylinders aligned along the field lines. Hydrogen atoms become roughly 1,000 times longer than they are wide, needles instead of spheres. Every chemical bond, every molecular geometry, everything that makes chemistry what it is, depends on the three-dimensional shape of electron orbitals. None of that chemistry operates normally here. The periodic table, as a guide to how atoms bond, becomes unreliable. The vacuum itself changes. Quantum electrodynamics, the theory of how light interacts with charged particles, predicts that in sufficiently strong magnetic fields, the vacuum becomes birefringent. Light splits based on its polarization. One component travels faster than the other through the magnetized vacuum. Empty space near a magnetar behaves optically like a crystal, bending and splitting light not through matter, but through the structure of the vacuum itself. This effect has been observationally confirmed near a neutron star. The quantum vacuum is physically modified by the field strength. Now, the 1,000-kilometer lethal distance. At that range, the field from a magnetar is still strong enough to disrupt the quantum mechanical structure of the atoms in your body. The iron in hemoglobin, the calcium in your bones, the electrical signals in your neurons, all of these depend on specific atomic and molecular arrangements that the field destroys. Not through heat, not through particle radiation in the usual sense, through direct magnetic disruption of biological chemistry at scales smaller than cells. You wouldn't burn, you wouldn't be vaporized. The atoms that constitute you would simply stop being arranged in the way that makes you a functioning biological entity. At 1,000 kilometers, from something the size of a city. There's nothing else in the universe that does this. Not a black hole. A black hole's danger is gravitational, tidal, proximity dependent in a different way. Not a supernova. A supernova's lethality is heat and radiation, which dilute with distance. A magnetar's field is something categorically different. It reaches out and reorganizes matter through a mechanism that doesn't dilute the same way at close range. How does something like this form? The short answer, the same way ordinary neutron stars form, the core collapse of a massive star. When a star between roughly 10 and perhaps 40 solar masses exhausts its nuclear fuel, the core collapses in under a second, bounces, and explodes as a supernova. The neutron star is what remains. The question is why some of these remnants end up with magnetic fields 1,000 times stronger than others. The collapse physics is the same starting point. The initial conditions of the star must be different, but how? The leading explanation is the dynamo mechanism. If the collapsing core is rotating fast enough and has convective turbulence at the right spatial scale during the first second of its existence, a brief but ferociously efficient dynamo process can amplify the magnetic field by orders of magnitude. The window for this is milliseconds. The field that emerges from those milliseconds determines whether the resulting neutron star is a magnetar or not. Alternative candidates: differential rotation during collapse, where different layers of the progenitor star rotate at different rates, winding and amplifying field lines. Or pre-existing strong fields in the progenitor star, amplified during compression. Here's the honest problem. We cannot observe a collapsing stellar core. The event happens too fast, the interior is opaque, the physics at those densities is modeled, but not directly testable. We work backward from the magnetar's observed properties and ask what initial conditions could have produced them. The answer is constrained but not unique. There are approximately 30 confirmed magnetars in the Milky Way, out of roughly 3,000 known neutron stars, about 1%. Either magnetars are genuinely rare products of unusual initial conditions, or they're common, but we can only detect them while they're young and active. That second possibility matters. Magnetar fields decay. The extraordinary magnetic energy is gradually released in bursts, in flares, through resistive dissipation over roughly 10,000 years. After that, the field has weakened enough that the magnetar becomes an ordinary pulsar and eventually goes silent. Every magnetar we can currently identify is, on cosmic timescales, a newborn. The old ones are invisible to us. Now, the crust cracking, because this is where the most dramatic events come from, and the physics is worth dwelling on. The magnetic field inside a magnetar is not frozen in place. It evolves, it shifts. As it evolves, it applies stress to the neutron star's crust, the nuclear pasta layer. Stress accumulates over years. The crust, the strongest material in the known universe, resists. And then, at some point, it doesn't. A starquake. The crust fractures. A sudden displacement, possibly just millimeters, possibly a centimeter or two across a fault, releases energy stored in the stressed field. The release is not gradual, it's sudden, violent, and it propagates outward through the magnetosphere in Alfvén waves, magnetic disturbances that accelerate charged particles to relativistic speeds and produce bursts of gamma rays and X-rays. The energy released in a major starquake can equal the total energy output of the Sun over 100,000 years, released in a fraction of a second. Think about that displacement, millimeters, on an object 20 kilometers wide. Millimeters of movement in the strongest material in the universe produces an explosion equivalent to 100,000 years of solar output. The December 2004 event came from exactly this, SGR 1806-20, a magnetar in the direction of the constellation Sagittarius on the far side of the galaxy, 50,000 light-years away, experienced a giant flare. Not a typical burst. Giant flares are a rare, distinct category, more energetic by orders of magnitude than ordinary magnetar activity. In 0.2 seconds, SGR 1806-20 released more energy than the Sun produces in 250,000 years. Every gamma-ray detector in space was saturated. Instruments designed to measure the most energetic events in the cosmos, gamma-ray bursts from collapsing stars, neutron star mergers, events at cosmological distances, went completely blind. The flash was too bright for the instruments to resolve. A burst from within our own galaxy, from an object the size of a city. The initial pulse hit Earth's atmosphere and ionized the night-side ionosphere. Radio communications were disrupted. Earth's electromagnetic environment was measurably altered by an event 50,000 light-years away. If that event had occurred within 10 light-years of Earth, well within the range of potential stellar neighbors, the gamma-ray dose would have stripped our ozone layer and irradiated the surface to levels incompatible with complex life. A mass extinction trigger. From the other side of the galaxy, from something 20 kilometers wide, the closest known magnetar is SGR 1935 plus 2154, roughly 30,000 light-years away, safe by distance. For now, safe by the luck of where in the galaxy we happen to be. That same magnetar, SGR 1935 plus 2154, did something else in April 2020 that solved a different mystery entirely. For years, astrophysicists had been puzzled by fast radio bursts, FRBs, millisecond pulses of radio waves arriving from cosmological distances, implying source energies of extraordinary magnitude. No confirmed source, dozens of theoretical candidates, a genuine open question in observational astrophysics. On April 28, 2020, SGR 1935 plus 2154 produced a fast radio burst detectable from within our own galaxy. For the first time, an FRB was caught with an identified source, a magnetar. The burst was less energetic than the cosmological FRBs by several orders of magnitude, but the mechanism was the same class. Magnetar activity, through a process still not fully understood at the level of microphysics, converts magnetic energy into coherent, narrow-band radio pulses that travel across the universe essentially undiminished. One object, flaring at different energy scales, affects Earth's ionosphere at 30,000 light-years and produces signals detectable with radio telescopes at distances of billions of light-years. The range of a magnetar's influence spans from planetary to cosmological. That's not a metaphor, that's measured physics. Now let me go inside, because what a magnetar is on the interior is where physics reaches its honest limits, the outer crust, exotic neutron-rich nuclei deformed by the magnetic field into cylindrical shapes impossible in any laboratory. The inner crust, free neutrons, possibly forming a quantum superfluid, frictionless, rotating without viscosity, carrying angular momentum in quantized vortices. The outer core, neutron superfluid coexisting with a proton superconductor, producing persistent currents that generate and sustain the magnetic field at stellar scale. The inner core. This is where the equations stop agreeing with each other. The density exceeds anything achievable in any particle accelerator on Earth. Possible states of matter include hyperons, particles containing strange quarks, appearing in bulk matter under compression, pion condensates, kaon condensates, quark-gluon plasma, individual quarks no longer confined inside protons and neutrons, moving freely as a collective state. We cannot test these conditions in any experiment. We infer the interior from external behavior, spin rates, cooling curves, burst characteristics, timing glitches. The inference is constrained, it's not confirmed. We have a set of models consistent with what we observe, and we do not yet have the data to choose definitively between them. The most extreme object in the universe, and we're still building the theoretical vocabulary to describe its interior. That's the honest position. But what magnetars give us, even with this uncertainty, is irreplaceable. Quantum electrodynamics in the strong field regime, the vacuum birefringence confirmed near a neutron star, tests QED at field strengths 10 orders of magnitude beyond anything achievable with human-built instruments. The standard model prediction, verified in conditions we cannot create. General relativity operating on a surface where gravity is 200 billion times Earth's, where time runs measurably slower than a few kilometers above the surface, where photons leaving the star are gravitationally redshifted in real time. Dense matter physics, every burst, every glitch, every cooling measurement is a constraint on what happens to matter under conditions the universe offers and we cannot manufacture. These constraints are how we build toward understanding the deep interior, slowly, carefully, honestly. Every magnetar detection is a physics experiment run by the universe in conditions we cannot replicate anywhere else. Now let me tell you what I think is worth carrying away from all of this. 20 kilometers wide, more massive than the Sun, wrapped in a magnetic field strong enough to deform the quantum vacuum, occasionally cracking by millimeters and releasing more energy than the Sun produces in 100,000 years. 30 of them active in our galaxy right now, aging, flaring, unpredictable. The one that fired in 2004 was on the other side of the Milky Way, half a galaxy away, and it still reached us, changed our ionosphere. Not catastrophically, the distance protected us in the way that a wall of space protected us, but it reached us. Distance is not the guarantee we think it is. What we depend on for safety from magnetars is not physical shielding, it's the dilution of energy across light years of space. And the 2004 event reminds us that dilution across 50,000 light years can still produce a measurable effect. Here's what I keep returning to. Magnetars exist at the intersection of every extreme the universe can stack simultaneously. Maximum density short of a black hole, maximum magnetic field, maximum gravity outside a singularity, quantum mechanics, general relativity, and nuclear physics. 3 frameworks that we still don't know how to fully unify, all operating together in the same 20-kilometer object, in conditions we cannot reproduce. They are the universe stress testing its own laws, pushing its own physics to the edge of what the equations allow. And occasionally they fire, and the pulse travels across the galaxy and arrives at a small rocky planet where organisms have built detectors sensitive enough to record it, analyze it, and slowly understand what produced it. We've named the most dangerous object in the known universe. We've watched it fire. We've felt it reach across the galaxy. We still don't fully know what's inside it.